Today we are going to new chapter. Namely, chapter 6. That is a power of randomization. What is randomization? Randomization just means just using random numbers. It's pretty simple. And we already had a couple of cases that random numbers play an important role. For example, just remember we have two parties and communication between them, and one guy is trying to convince the other guy that he knows the answer without leaking information. So this is zero knowledge. Zero knowledge. I don't know. Proof. And in that system, in that mechanism, random numbers did play a very important role. So without random numbers, we can't recognize, we can't make the system work. Yeah. So random numbers, you already know that the random numbers are very important. But in this case, our main topic, our main focus was not on the random numbers, randomization, but information hiding. This was our main topic. But from today, now we changed our gear a little bit, and our main, we're gonna more directly focus on randomization, random numbers. Okay. So let's go to the first example. First example is the locker game. This is a famous puzzle. Yeah, this is a famous puzzle, and this is really good example to see, how powerful the random numbers are. Okay, so in this problem, random numbers really play an important role. Okay, what is the game? It's pretty simple. We have a locker room. We have 10 lockers. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, we have 10 lockers. Of course, in the locker is just a box. And each locker has a door. And door is closed. All doors are closed, normally. So if you open the door, then you can look at the inside. Okay, that is locker. And inside the locker, we have names. 1, 10, 8, 3, 9, 4, 2, 6, 7, 5. Okay, I'll explain the rule of this game. This is a team game. It's a team game, and a team of 10 people, and plus referee. So you have one referee, and a team of 10 people just do this game against the referee. Okay? The referee, okay. Each locker has a name of a player. So each locker has a name of one of the 10 people. So this locker, for example, has name 1, name 10, name 8. Okay, so we have 10 people whose name is just a number between 1 and 10. Okay. Oh, this is important. Each player enters a locker room just one by one. No two people, no two or more people can enter the locker room at the same time. You have to enter the locker room by yourself. Okay, this is very important. Once you enter the room, in the locker room, okay. Once you, I'm sorry. Once you are in the locker room, you can open at most 5 lockers. Okay, at most 1/2 of the lockers. If you can find your own name, you win. If all 10 people win, the team win. Team wins. Okay. So I hope you understand the rule. We have a locker room, and inside the locker room, we have 10 lockers. Of course, all lockers are closed, so you can't see the inside of the locker. Now, you are one of the 10 people. Okay, you make a team, and you are one of them. You can enter the locker room just by yourself, one by one after another, and you can open at most 1/2 of the lockers. In this case, you can open 5 lockers. And if you can find your own name, you win. Okay? You can't find your own name, in those open 5 lockers, then you lose. And all 10 people win, the team wins. Okay? Okay, now you understand the rule. But there's another important rule. Here, okay, so this is a very important rule. Just remember, this is a team game. So of course, the team can discuss their strategy before the game. But once the game started, no communication is allowed between the players. Okay? This is a very important rule because if there is no such a rule, then you can cheat. For example, the first guy just enters the room, okay? Then the first guy opens maybe the first 5 lockers. If he does not find his name, then the game ends. But if he can find his name, then for him everything is clear. The locker, the first 5 lockers, you can talk to the other guy, okay, by your cell phone, that the first 5 lockers have this name, this name, this name, this name, and this name. Okay? So of course, all the other guys can win. That means if there is no such rule, then the game is not so interesting. But because of this game, because of this rule, the game becomes much more interesting. Okay? So once again, you can discuss your strategy before the game, but once the game started, you can't communicate with each other. Okay? So that means one guy enters the room, then this guy just exit from the other side. Okay? Enter, exit, enter, exit, enter, exit. No communication between the players at all. Okay? Good. Now, let's see a couple of strategies. Strategy 1. Strategy 1, all players, they can discuss their strategy, then decided their strategy. That is to open the first 5 lockers. All guys open the first 5 lockers. What about this strategy? Is it good? This is obviously bad. Because all players open the first 5 lockers, meaning one half of them cannot find their names. That means the team never wins. Because in order to win, all guys should win. Okay? It's totally impossible. This is bad. Bad. Obviously bad. Strategy 2. What about this one? So even numbered players open even numbered lockers. Odd numbers. Odd numbered players open odd numbered lockers. So for example, number one player open 1, 3, 5, 7, and 9. Number 6 player open 2, 4, 6, 8, 10. What is this? What about this strategy? Again bad. Again bad. Because the referee, when the referee put those names into lockers, he knows their strategy. So that means, of course, he puts even number into odd lockers. then no one wins. Oh, this is bad. Just remember, we are already discussing the worst case. That means this strategy cannot win at all. Totally impossible. Now you can see any deterministic strategies are bad. It doesn't work. Deterministic means the algorithm decided deterministically. The algorithm runs in deterministic fashion. Okay? No deterministic algorithms can win. Well, that's why we need some kind of randomization. Now, strategy 3. Probably this is the most natural. This is the most natural strategy. Each player opens 5 lockers at random. This is the most natural strategy because we don't have any information. Which lockers have which numbers. We don't have any information. Then what we can do is maybe this one. Each player opens 5 lockers at random. Okay, but what is the success probability? Success probability is this. 1/2 to the 10. Why? Each player opens 5 lockers at random. That means each player wins with probability what? 1/2, of course. And for the team to win, all 10 guys need to win. That means 1/2 to the 10 is success probability. This is very small, something like 1/1000. Okay. This is better. This is better than the previous strategies because the success probability is positive. Positive. The previous strategy, success probability is 0. Success probability is 0. This is a positive, so this is better. But, well, this is very small, 1 over 1,000. Very small. And if the number of players gets larger, then this success probability gets worse. Okay? Well, this is better, but not very attractive. But can you think of a different strategy? We have no information. Which number is in which locker? Completely no information. What can you do? Can you imagine any other strategy to make this probability larger, better? We do have amazing strategy. We do have amazing strategy. I'll show you amazing strategy. Okay. Okay, this is a strategy. All players share a single random permutation of 1 through 10. Just a random permutation of 1 through 10. Just select, throw dice, and select one random permutation of 1 through 10. For example, 5, 7, 2, 10, 3, 4, 1, 9, 6, 8. And just, you write down this permutation on a small piece of paper, then you enter the room. Once again, just select one single permutation, and then you memorized. You memorized it, or you write it down on a small piece of paper, then you enter the room. After you enter the room, what you do is this. Okay? Now, this is important. This is your random permutation. Then you change the number of lockers. You change the number of lockers. Just like, 5, 7, 2, 10, 3, 4, 1, 9, 6, 8. So you change the number of lockers from the original one to your random permutation. Then what you do is this. You open your locker. You open your locker. So suppose that you are number 5. Okay? Suppose that you are number 5. Then you open locker 5. Locker 5 is here. Then you find 1. Oh, bad. It's not your number. But then you open number 1 locker. Number 1 locker. Okay, so 5 goes to number 1, then you find 2. Oh, bad. Bad. Now you open number 2 locker. 8. Bad. Bad. Now you open number 5. Okay, 5. 8 locker. Oh, okay, good. You find your number, or maybe once again. Suppose that you are number 5. Then, okay, number 5 locker, then 1. Okay, 1, 2, 2, 8, 8, 5. You find your number. You win. How many lockers you opened? 1, 2, 3, 4. No. 5, 2, 8. Oh, okay. Only 3. Only 3. Only 3. Okay? So, suppose that you are 6. Okay? Your number is 6. You open 6, 7, 7, 10, 10, 3, 3, 3, 9, 9, 6. You win. Okay? Again, you opened 1, 2, 3, 4, 5 lockers. So you win. Because you can open up to 5 lockers. What's going on? What's going on? It looks like it's magic. It's magic. Well, actually, it's all guys win. All guys win. Why? Because suppose you're number 2, then you win on this cycle. Suppose that you are 3, you win because you can follow this cycle. All guys win. Do you believe that? Believe or not? This is a fact. All guys win. Okay. Let's do analysis. Let's do the analysis. Okay? The team. Loses. Now you know that once you determine one permutation, then the whole thing, then this 10 locker will be partitioned into cycles. Okay? In this case, in that case, the whole 10 lockers are partitioned into cycles of length 3, length 5, and what else? What else? 1. Yes, 1. 1, 2. No. Something strange. 1, 2, 2, 8, something strange. 1, 1, 5, 5, 1, 1, 2, 2, 10. Oh, something strange. This is bad. 6, 6, 6, 7, 7, 7, 10. Oh, this is bad. I'm sorry, this is bad. Sorry. You have number 5, then 1. Okay? The 1 is 2. The 2 is 8. 8 is 5. Sorry. And again, this is also, it's okay? So what else? 4, 4, 4. Okay, so in this case, if you choose this permutation, then the whole 10 lockers will be partitioned into 3 cycles, whose length is 1, 4, and 5. Okay? If you select different permutation, then there may be a cycle of length more than 5. In that case, you lose. Okay? You can make sure. Just try to, just check different permutations. Then maybe you can find a cycle of length 6 or more. Then you lose. You lose. That means okay. Let's calculate the probability that there is a cycle of length 6 or more. Okay. So a given random permutation. One through 10. And the probability, we're going to calculate the probability that there is a cycle of length 6 or more. Okay. Okay, what we are doing is to change the number of lockers at random. To change the number of lockers at random, but to make things easier, from now we consider we are just giving a random permutation here. The number of lockers is fixed. Okay, the number of lockers is fixed: 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And inside the locker, we are given a random permutation. This is exactly the same. Okay? In this game, actually, we are change the number of lockers at random. But now for analysis, we don't change the number of label of lockers, but inside given completely at random. This is exactly the same thing, right? Okay. So now suppose that given a random permutation here, Okay, inside the inside locker, we have a random permutation, something like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Then we just calculate the probability that there is a cycle of 6 or more. Okay. Now, suppose that there exists cycle of rank 6. Okay. Now, we are now calculating the number of cases such that we have a cycle of rank 6. Cycle of rank 6, first of all, the selection, we need a selection of those 6 numbers. The number of possibilities is just 10 choose 6. Okay? We have this many possibilities for choosing 6 numbers. Then, number of different cycles of such 6 numbers is 6 factorial divided by 6 is 5 factorial. We just decided 6 numbers, then the cycle of those six numbers is a permutation divided by 6 because the rotation is the same. Okay, so this is a number of different cycles. Number of different cycles. So, for example, we have 6 numbers. Okay, 1, 3, 4. Oh. We selected 1, 3, 4, 5, 9, and 10. Okay, 1, 2, 3, 4, 5, 6. We selected 6 numbers. Then the permutation. Okay, the cycle here we something like 5, 9, 1, 3, 10, 4. Okay, just just one. This is one cycle of those 6 numbers. Okay, the cycle. Now, once you decided this cycle, then the placement of these numbers are fixed. Why? Because local 5 needs to include 9. Local 5 needs to include 9. And 9 should have 1. 1 should have 3. 3 should have 10. And 10 should have 4. And 4 should have 5. Right? So once you decided this cycle, then the placement of those numbers is completely decided. Completely decided. So no further choice. No further choice at all. Okay? But the remaining 4 lockers are arbitrary. Remaining 4 lockers are arbitrary. remaining 4 lockers are arbitrary. So that's why that we need 4 factorial different permutations. The remaining 4 numbers is fixed, but the order is completely arbitrary. So we have 4 factorial. That means okay. Okay, now that we can calculate the total number of permutations having a cycle of length 6 is a product of this number, and this number, and this number. Product of this and this and this. Okay, then it's a pretty simple calculation. And that is 10 factorial divided by 6. And that means maybe can use that's aside. Erase. Therefore, the probability that the cycle of length 6 exists is just 1 over 6, because the total number of cases is 10 factorial. Okay? So just divided this number by 10 factorial, then we have the probability 1/6. We can do the exact same calculation for the cycles of length 7, 8, 9, 10, and the probability that we win, we lose, we lose. Equal okay. We can do exactly the same calculation for the cycles of length 7 or more. And actually, that probability for cycle of length 7 is just, this probability, this probability for length 7 is exactly 1 over 7. Complete the same calculation. And length 8 is 1 over 8, length 9 is 1 over 9, and 1 over 10. So we sum up all these probabilities, then we can get the probability that we lose. That means we win with probability something like 0.35. Oh yeah, you have a chance of winning. You have a chance of winning something like 35%. This is amazing. It's amazing. Okay, just remember that I just erased, but not erased. Yeah, here. here. This is a kind of a standard, a kind of a normal, usual strategy. Then your winning probability is tiny, almost zero. But if you use this amazing strategy, then your success probability is something like a 35%. It's really amazing. Furthermore, you have N players, you have more players, but you still enjoy a good okay. So even if you have many people, your losing strategy is exactly like this: n plus n, 1 over n plus 1 over n plus 1, and so on and so forth. Okay? Then, so this is that n is equal to what? 5? I don't know. Okay? So the calculation is something like this. Then this number is less than, at most 0.7. That means your winning probability is still something like 30%. Okay? Now, this is really amazing. If you use a kind of a natural or elementary or kind of a standard, kind of a common sense, then your winning strategy is really tiny. But if you use this amazing strategy, is you can win with something like 30%. It's really amazing. Okay, good. So this is the power of randomization. This is exactly the power of randomization. Now, I'm going to the second example. So Ramsey number. Okay. A given K5. K5 means a complete graph of 5 vertices. Complete graph of 5 vertices. 1, 2, 3, 4, 5. Complete graph means we have edges between any pair of vertices. This is a K5. Okay? Any pair of vertices, you have edge. Now, color. Okay, your task is to color each edge in blue or red. But the condition, we have condition so that no Okay. So your task is to color each edge in blue or red so that no triangles of the same color appear. Okay. Is this possible? Yes. I'll show you. Oh, first of all, what is the triangle of the same color? You know, if just you color red and blue. Red and blue. And if you have a triangle of red, then you lose. Like this. Okay? Then you lose. So you have to avoid. You have to avoid this kind of a triangle of same color. Okay? Now, what you do? Once again. Okay. So this is K5. And I'll show you, you know, the coloring of edges without any triangle of the same color. Does anyone want to try? Would you like to try? You have no idea? Does anyone want to try? No triangle of same color. Would you like? Okay, please. Great. No triangle of the same color. Thank you very much. Now, we are given case 6. Do the same thing. Now, you have case 6. Case 6. Do the same thing. Possible? No. Okay. You can try. I'm sorry. One edge is missing. Yeah. So you can try. You can make sure. It is impossible. It is impossible to do the same thing. Okay. Just let me try. Okay. Maybe red. Then should be blue. And maybe blue should be red, and red, so should be blue, and blue. What else? Maybe red and blue, red. I'm tiring. Okay, anyway, it's impossible. It's impossible. So you finally get stuck. you'll finally get stuck. Then it's impossible to color K6. Okay. So what is the Ramsey number? Definition of Ramsey number. Okay. So this is the definition of Ramsey number. Ramsey number R of K and K, Y2K. So, okay, this is a little bit complicated, but just ignore Y2K. Just ignore the reason. Okay. RKK is equal to the minimum number n, such that for any coloring of Kn, there must be a single colored KK. Means, for example, R of 3 is equal to 6. Meaning, if n equals to 5, then there exists coloring of no single colored K3. But n to 6 then does not exist. That does not exist means minimum n such that for any coloring, single colored K3 triangle appears. Okay, so that's why R of 3 is 6. Okay? For any coloring of K6, you can't avoid K3, single colored K3, single colored triangle. Okay? That means R33 is 6. Okay, I'm sorry, minimum n. Because n is equal to 5, then you are successfully coloring. Okay. Now, why? Why randomization? How randomization comes in? Well, so far, there's no random number. There's no randomization at all so far, right? We don't have any randomization. Why randomization is important in this problem of the following theorem? Now we have a theorem. R of kk is something like exponential. Something like exponential. Okay. When k is equal to 3, when k is equal to 3, this low bound is not so good. Not so good. R33 is actually 6, but 2 to 2 to the 1.5 is smaller than 6. So when k is equal to 3, this lower bound is not so good. But for larger k, this number is exponentially growing. Okay? But where is the randomization? Where is the randomization? No randomization at all. But okay. Okay, you're going to prove that if n is equal to this number, then there is a successful coloring. That means R of k is greater than that number. Now I'll show you a very simple coloring algorithm and its analysis. Our goal is, we have a successful coloring. We have a successful coloring if the number n is that big. Okay. Algorithm is very simple. Our algorithm is very simple. Just color each edge at random in blue and red, blue or red. You were given a kn, and vertices complete graph, like that. Then just color each edge at random. In blue or red. Now randomization came in at random. Then Now, we do the following analysis. Let's compute. We compute the probability that this algorithm fails. That means, you're going to have a single colored KK. If you have a single colored KK, you lose. So this algorithm fails. Compute the probability that this algorithm fails. But it turns out that this probability is exactly less than 1.0 if n is equal to that value. Meaning, this means we can conclude that this algorithm succeeds with non-zero probability. Means okay. This algorithm, succeeds with non-zero probability. That means there must be a successful coloring. Okay, we are done. Because there exists, our goal is to show that there exists a successful coloring. But we did that. There must be a successful coloring. We are done. Okay. So our remaining task is just to calculate probability P. Okay. We don't have much time, so let me go a little bit quickly. But this is just a very simple calculation, so you don't have to worry about this. Okay? The probability is less than 1.0. This is pretty easy. Okay, so you have a graph. And just you select a fixed kk. You just select arbitrary kk. Then the probability that this kk is single colored is pretty easy. It's pretty easy because just color each edge at random. We have n choose k edges. So the probability that all edges are colored in red is 1 over 2, 1/2 to the k over 2, 1/2 to the number of edges, right? All edges, the probability that all edges are colored in blue is exactly the same. So this 2 is red or blue. Red or blue. Once again, if you color each edge at random, then the probability that all edges are colored in blue is 1/2 to the number of edges, right? We have n vertices. We have n vertices in total. N vertices in total. So the way of selecting such kk is, of course, n choose k. So the probability that at least one single colored kk appears is just a product of those two numbers. This is what we call union bound. Union bound. If the probability that A or B happens is at most the sum of probabilities that A happens and B happens. Okay? So this is at least one single colored kk appears is at most the product of these two numbers. Now, we are almost done. Just recalculate this value. I'm sorry. This is n choose k, just n factorial divided by k factorial and n minus k factorial. And this 2 to the 1 minus k to 2 is just this number. Just this number. Or just, the simple calculation. And we change this n factorial to don't know. So it's n factorial divided by n minus k factorial is less than n to the k. Okay? N factorial divided by n minus k factorial, is less than n to the k. Okay? Just change the position of numbers. Then this is much less than 1. And this is 1. If n is equal to 2 to the k over 2. So we can conclude that this is 1 point. Done. We are done. Okay? What we did is very simple. We just calculate the probability P that this algorithm fails. But this algorithm fails with probability exactly less than 1.0. That means this algorithm succeeds with positive probability. That is enough. That is enough. Because if this algorithm succeeds with a positive probability, then we can conclude that there is a coloring. There is a required coloring. Good. Good. So, in this case, the theorem has nothing to do with randomization. But the proof, it's really, really clever. We did use randomization in the proof of this theorem. Okay? So this is a completely different way of using randomization. We use randomization for proofs. Importantly, actually, this probability P is much. In fact, that the probability P is much less than 1.0. Almost there. That means this simple algorithm almost always succeeds. Okay? So this is also important to know that this simple algorithm is quite strong. Just try to think that your task. Your task is to color this graph without any triangle, single colored triangle. But K5 is maybe easy, but even for K6, that is not so easy. But you can use that simple algorithm. You don't know how to do that. But if you just randomly color each edge, then it's almost always good. Really amazing. So in some cases, completely random algorithm, very simple algorithm, works pretty well. Okay, good. So this is the power of randomization. Today, I showed 2 examples about the power of randomization. That is really, really amazing. Next week, I'm going to show you a couple of different examples where randomization is more directly works. Okay? So see you next week.